Okay, let us do a couple of problems on the concept of stress and traction. So, in the first problem that we're going to do, you have a Euler-Bernoulli beam, the kind that you have done in your MOS course. So, it's subjected to end moments. So, these are the end moments. So, these are the end moments. So, these are going to bend this into a shape like this. Okay, so it's subjected to these. Erase this. Okay, and the only component of stress, we know that in this problem the only component of stress is in the one direction, and for the basic Euler-Bernoulli beam theory without the shear corrections, sigma 1 is the only component of stress. Okay, so our beam, for simplicity's sake, has a square cross section of h by h. Okay, and now what we are going to do is, okay, one more thing is that we assume in the Euler-Bernoulli beam that things don't vary in this direction. In the x3 direction, in this direction things don't vary. So everything is a function of x1 and x2 only. In the x3 direction, there's no variation of the stresses. The stresses are invariant in the x3 direction. They're functions of x1 and x2. Only x1 and x2. So the let us take this red plane that I have drawn here, and the obviously the normal to the red plane is this, and this is equal to E1. This is the normal to the red plane. And if I apply the Cauchy relation, which remember was Ti equal to sigma Ji Nj, my N1 is 1, N2 is 0, and N3 is 0 as well. So T1 is, and only sigma 1 is not equal to 0. All other sigma ij is equal to 0. So T11 is sigma 11 N1, sigma 1 sigma 21 n2, and all those things are 0 because n1 n2 n3 are 0. So this is equal to sigma 11. T2 is equal to 0. T3 is also equal to 0, which means your traction vector is sigma 11 E1. It's like here. So the traction vector on this plane is equal to sigma 11 E1. Now let us cut the beam at that plane, and so we have this kind of a situation. We have these moments applied on this end. These are the external moments, and then we have internal forces, which is this traction T, which is due to the part that we have cut off. So this part that we have chopped off is exerting this force T on the part on the left, and T is equal to, as we have found from the Cauchy relation, sigma 11 E1. So it's directed in this direction, and we have denoted it by E1, and X is X1, X2. X1, X2 is a point here. It doesn't depend on X3. So now, how do we go about finding T? So T should be such that if I take the integral of T over, so if I take T ds and integrate it over this whole area of the cross section, which is a square in our case, if we integrate it over this whole area of cross section, we should get 0 because there's no force applied on this. So the force balance should give the total force due to this equal to 0, and the moment balance will be that if this point on the cross section, this point has x, and t is out of the plane, and t is out of the plane, so x cross t will be the x cross t ds would be the moment due to a small element here on this area ds. If you have t as the traction, then x cross t is the moment, x cross t ds is the moment, and that integrated over this area, over the cross section area, is the total moment of this force, of this distribution of forces, and that has to balance me3. So this is the moment balance equation. So these two equations have to be satisfied by your t, and we can simplify this a little bit. So let me draw this a little bit more carefully, the cross section. So this is the cross section, minus h to h, and then minus h to h again. This is your x2 axis, and this is your x3 axis. We have a small element here which we call ds, and ds can be taken to be x2 x3, so dx2, so this is dx2, this is dx3. So x is the vector here, so x cross t dx2 dx3, I replace ds with dx2 dx3, integrated from minus h to h and minus h to h will give you the total moment, and that this x cross is, when you work it out, it will come out to be, so x is x1 e1 plus x2 e2 plus x3 e3. So x is the vector from here to this point. So this is your x. So the projection of that x is this. So it is x1 e1 plus x2 e2 plus x3 e3. So if you draw the, so this is your plane. So this is your x. This is the projection of x. In the 1, 2 plane, this is the projection of x in the 2, 3 plane. So x is given by this, and t is, remember, t is sigma 1 1 e1 only. So x cross t, if you work out x cross t, you will get x3 t1 and x2 t1, where t1 is sigma 1 1 in both cases. So this would be your, this would be the moment. So this has to be equal to me3. Now also the first one would mean so this would mean that this integral is equal to 0. Okay. Now here, if you look at it carefully, you will see that t1 is a function of x1 and x2. So t1 equal to sigma 1 1 is a function of x1, sorry, is a function of x1 and x2. It's not a function of x3, which means that this, when integrated from minus h to h, has just x3 in it. So this turns out to be 0, and you are left with, sorry, this turns out to be 2h, this turns out to be 2h, and you are left with these two integrals. So now you are left with only an integral in dx2. So this is the force balance, and this is the moment balance. You get this 2h because things don't vary in the x3 direction, and this integral here, x3, t1 is not a function of x3, so when I take this integral, you get 2h out. So you can do the integration over x3 in a very trivial manner. It gives you 2h, and you are left with these two. So these two are the equilibrium equations that these two are equilibrium equations that you get from your force balance that tell you what are the conditions that sigma 11 must satisfy on that red plane. Remember, T1 is equal to sigma 11. So we are basically asking what is the form that T1 should have in order to not violate equilibrium. And the answer is that it should satisfy these two equations. Now, what kind of a function sigma 11 would satisfy these two equations? Now, what we are saying is that over the cross sectional area, T1 varies in a manner like this. This is x2, this is x1, and this is x3. So T1, what we have here, dx2 is, let's say, this small segment. This is actually all across. So this small segment is dx2, and T1 or sigma 11 do not vary with in the x3 direction, so it's invariant in the x3 direction. So sigma 11 x2, so T1 dx2, which is same as T1 dx2, is actually T1 times this area. So T1 dx2 into 2h is T1 times this area, and so dx2 into 2h is this area, and that gives you the total force, and the integral here gives you the total force that is acting on this 2h by 2h cross section of the beam. So this basically tells you that the net force, the total force on this cross sectional area has to be equal to 0. And this tells you that x2 sigma 11 dx2 into 2h, dx2 into 2h is this area again, and T1 times this area is the force. So T1 times dx2 into 2h is the force acting on this area, times x2 gives you the moment about this axis, about the x3 axis. So I'll have to draw the area again. So this area is 2h into dx2. So this into sigma 11 gives the total force acting on it, and then times x2 is the area, is the moment of this small force about this axis, about the x3 axis. So that moment has to be equal to the applied moment that is applied at the left edge of the beam. So we are looking for an arbitrary distribution, which is arbitrary to the extent that it's not a function of x3 that we have assumed already, but we are looking for an arbitrary distribution of x1, which is equal to T1 in this case. We are looking for an arbitrary distribution that satisfies these two equations, the moment balance and the force balance. Obviously, there can be many such distributions. However, Euler-Bernoulli assumed a very clever distribution, which is this, what you read in your MOS courses. They assumed that it varies linearly with x2. The distribution of T1 varies, T1 or sigma 11 varies linearly with x2, and it is 0 at the neutral axis, which means that this equation as well as this equation is obviously satisfied for this distribution. Now, if this distribution was like this, then too this would be satisfied, but the linear one is the simplest distribution that sigma 11 can satisfy in order as not to violate equilibrium. So Euler-Bernoulli's assumption has to do with the fact that it's the simplest distribution that doesn't violate equilibrium in case of a beam which is subjected to a bending moments at the ends. Now, let us just quickly go through what we have done. Uh, what we have done first is we have figured out what is the traction on this. What is the traction on this? And to do that, we have said that okay, the only stress is sigma 1, 1. So what is the traction? So we figured out that the traction is such that T1 is sigma 1, 1 and T2 and T3 are both equal to 0. And that is because the normal to this plane is 1, 0, 0. So that is the first step that we did. We got the traction vector. Traction vector is along the normal and it is equal to sigma 1, 1. And then we asked ourselves, what is the condition that this traction vector must satisfy? And then we come up with the conclusion that it must satisfy these two equations. This is for force balance, this is for moment balance. And then if it has to satisfy both these equations, then one possibility, one of the many possibilities could be that it is a linear function with 0 at the neutral axis, so that the total force, here it's compressive, here it's tensile, so the total force is equal to 0 when integrated over the cross-sectional area, and the total moment is equal to m. The moment of this part and this part both add up, so the total moment is equal to m. So from this we can find out sigma 1, 1, which you know from your Euler-Bernoulli beam theory, sigma 1, 1 would come out as m x2 by I. I is the moment of inertia of the cross section. So this is what sigma 1, 1 will come out to be from this equation. So the point that I wanted to make is that the Euler-Bernoulli beam theory is one of the many solutions that are consistent with our idea of tractions and stresses. So it's one of the many solutions of this. We'll see this Euler-Bernoulli beam problem in detail later when we solve the equations of elasticity. Let us take up another problem, a problem of two spheres which are in contact with each other. So here again, I'm trying to just the problem is meant to show you what exactly the tractions mean. So how do you calculate the tractions? How do you handle them? So in this case, let us neglect friction out of the plane. So there's no friction in the out of the plane direction here. And if you draw the free body diagrams of this, then the yellow ball exerts some kind of normal force, and due to friction in this direction, in the S direction, there's a friction force here. So I take a coordinate system which is N and S, and I concentrate on the green sphere. So the green sphere is subjected to a set of forces, set of normal forces, which is in the direction of the normal, and a set of tangential forces in the due to friction in the tangential direction. We have neglected friction in the out of plane direction, so we don't have any tangential forces in the out of plane direction. Now, if you want to calculate the traction, so let us assume that Fn is the normal force per unit area. Fn is the normal force per unit area. Then the traction vector would be given by this. Okay. So in the ns coordinate system, the traction vector can be written like this. What would the relation between the traction and the stress at a point right next to the point where the traction is applied will be? To find that out, we have to first decide which coordinate system we are going to work on. If we are going to work on the ns coordinate system, then we are going to apply T is equal to sigma transpose n in that coordinate system, so that n will have components 1, 0, 0. in the ns coordinate system, n has components 1, 0, 0, and therefore the tractions also will be given in the ns coordinate system. And if we do that, tn will turn out to be minus fn and ts will turn out to be minus fs. Okay. However, if we now choose to work not in the ns coordinate system but in the e1, e2, e3 coordinate system, then this normal does no longer have components 1, 0, 0, but it will have some components n1, n2, n3. And in that case, the components of traction, again calculated through this expression, again component calculated through this expression, will uh, will give you these three equations, where n1, n2, n3 are the components of the normal in the fixed Cartesian coordinate system. So this these tractions or these tractions, they are the ones that are applied due to the yellow body on the green body. So they are the ones that are applied in this region. Okay, that is my del Vt. So that's where the tractions are applied. And what this equation, the Cauchy relation gives me is the relation between this traction and the state of stress right next to the traction. It does not say anything about the state of stress inside the body. It says that right next to the traction, the relation between the traction and the state of stress at that point should be given by this relation. And then the traction can be found in a suitable coordinate system. For example, if I find it in the ns coordinate system, then it's a simple set of equations. T1 is in the ns coordinate system, T1 is equal to minus Fn and T2 is Fs. So if I do sigma transpose T, then uh, sigma transpose n, if I do sigma transpose n, then what I get is um, t in the nth direction is equal to minus fn and ts is fs. So this is what I get if I use the ns coordinate system. If I use the ijk coordinate system, then this is what I will end up getting. This is what I will end up getting. And this just shows that in different coordinate systems you may get different sets of tractions, but the traction vector itself remains the same. What I mean by that is Tn n plus Ts s, this vector is equal to T1 E1 plus T2 E2 plus T3 E3. Both these give you the traction. Both these give you the traction. And but when you find the components, it depends on which coordinate system you describe your normals in. You will get the components of the traction in the coordinate system in which you describe your normal n. Okay, so I'll stop here and I will take up a new topic in the next class.